All right, hi everybody. In this video, we'll discuss a theoretical method for constructing confidence intervals to estimate a population mean using the central limit theorem. And so to motivate our example, we'll use the storms data set, which is in the dplyr package. And so recall this data frame, storms, is a huge data set of tons of storm observations for storms that occurred in the North Atlantic. And we'll consider this data set our population. And in particular, what we're going to want to do is estimate the mean wind speed out of all storms in this data set. And we're going to imagine here that we actually don't have access to the full population, but instead we have one random sample of 36 observations, wind speed observations. And so from this sample of 36 observations, how can we construct a confidence interval to estimate the population mean wind speed of all storms that are in the population? So to begin, let's first run the code cell up above. That's going to first load the dplyr package, and then it's going to store the wind speeds into a vector called population. And now from this population vector, I'm going to pick a random sample of 36 wind speed observations. And here I've just set the seed so that I will get the same sample every time I run this code. It's always fun to turn that off and then actually see how the randomization is at play here. Each time you run this code cell without the seed set, you'll get a different random sample. But I've picked my random sample and I've stored it in this vector called my sample. And so the first question is asking me, okay, based on your sample that you've picked, what would be your first estimate for the population wind speed? So I've picked my sample randomly. We've seen that the sample mean is oftentimes a good, reasonable starting estimate for the population mean. So in this code cell, I'm going to calculate the mean of my sample, and I'm going to store this in X bar, and I'm going to print that to the screen. So I can see that my sample has a mean of 61.5 knots. So my initial estimate for the population mean would be 61.5 knots. It makes sense if I just have one sample. However, this would be very different if I picked a different collection of 36 storms. So I don't just want to give a point estimate like this, but I should account for the variability in this estimate due to the randomness in the sampling. And so that's the benefit of using a confidence interval, is that we can build some margin of error into the estimate, and we get a sense of how precise that estimate is. And before discussing how we can use the central limit theorem to construct a confidence interval, I want to just first quickly go through the code that could be used to generate a bootstrap percentile confidence interval so that we can compare our result using the central limit theorem to the previous bootstrapping methods that we've been using. So I'm just going to run the code. And the point is just to generate a bootstrap distribution. So this first code cell above is generating a bootstrap distribution for the mean when we pick samples of size 36. And then this code cell is pulling off the cutoffs for a 95 percentile confidence interval. So if we were doing bootstrapping as we've been doing up to this point, we would have a 95% bootstrap percentile confidence interval for the population mean wind speed, which would be between 51.25 knots and 72.36 knots. And we could take a look at these values marked on our bootstrap distribution. So what I want to discuss in this video is a different method for calculating confidence intervals that is going to depend on the theoretical central limit theorem, and we can compare the results we get using the central limit theorem to the results that we just got using bootstrapping. And so if instead of using bootstrapping, we use a parametric approach, which is going to assume that the underlying sampling distribution is modeled using the central limit theorem. And recall that for the central limit theorem for a mean, we have that the distribution of X bar values is approximately normal with a mean that's equal to the population mean, and the spread of the distribution, the standard error, we get by taking the standard deviation of the population, sigma x, and dividing by the square root of our sample size n. And so underlying the parametric method is going to rely on some properties of a normal distribution, because the central limit theorem tells us the sampling distribution is normal. So let's recall back when we first looked at a normal distribution, we had this empirical rule that told us approximately 68% of the values for a distribution which is normal are going to fall within one standard deviation from the mean. And 95% of all values are going to be within two standard deviations, and approximately 99.7% of all values in a normal distributed data set are going to fall within three standard deviations from the mean. So let's check the accuracy of this empirical rule a little more carefully before we start to construct our confidence intervals using a normal distribution. So this first question is saying, well, let's check the accuracy of the first claim that says 68% of the data is within one standard deviation of the mean. So here we're going to use the standard normal distribution with a mean of 0 and a standard deviation of 1. And if I want to calculate the probability that that we're within one standard deviation above or below, that's calculating the probability that z is bigger than -1, but less than 1. And in R, I could use p norm and take 1. I have a mean of 0 and a standard deviation of 1. And I'm going to subtract from that p norm -1, 0, and 1. And so for a standard normal distribution in R, I don't need to include these options for the mean and the standard deviation, but I will include them here just so it's clear that we're using the standard normal distribution. And so running this line of code, we can see that the probability that z is between -1 and 1 is actually a little bit bigger than 68%. It's 68.27%. And we can check the other claims in that empirical rule. 3b was looking at the claim that what proportion of the data sits between two standard deviations above and below. So changing the code from the z-scores of 1 and -1, we now change that to a 2 and a -2. And here we can see that the 95% is actually more precisely 95.45%. And lastly, the third claim in that empirical rule is what proportion of the data lies within three standard deviations from the mean. And in this case, the claim is that it's 99.7%. Here we can see more precisely, it's 99.73%. Point being is this empirical rule is really close, but it's not exactly precise. We've used a little bit of approximation here. So when we're constructing a 95% confidence interval, it's going to be useful for us to consider, well, what are exactly the cutoffs that give me 95% of the data in the middle? And so if I'm thinking about this picture, I have a normal distribution. If the middle 95% is between -z star and z star, that means in the left tail and in the right tail, below -z star or above z star, in those two tails is the missing 5%. And because the normal distribution is symmetric, that 5% is split evenly in those two tails. So in other words, the amount of area that is above the positive z star, that is 2.5%. So that's going to be 0.025. And the corresponding area below that z star value, therefore, is the other 97.5% or 0.975. So I'm going to enter that 0.975 into the Q norm function below, and the output tells me that the positive z star value is 1.96, and therefore the negative z star value is -1.96. And in between those two values sits the middle 95% of the area. So that 2 was a bit of a rough estimate, actually within 1.96 standard deviations above and below the center of the normal distribution, we have 95% of the data. Okay, so let's see how we can use this observation to help us construct confidence intervals to estimate a population mean. So question 4 is going to take us through the process. So I start with this observation that 95% of the values under a normal distribution are within 1.96, not exactly 2, but 1.96 standard deviations above and below the mean. So taking this inequality inside the probability on the right side, I can first replace z with the definition of what the z-score would be when we're working with a sampling distribution for a mean. So here our individual observations are the sample mean x bar. The center of that distribution we denote with mu x bar, and the standard deviation of that distribution we denote with a sigma x bar. So this is just the definition of a z-score. Next, moving down to the next step below, we're just using the central limit theorem that says when we're dealing with the sampling distribution for a mean, the sampling distribution is going to be centered at the population mean mu, and it's going to have standard deviation, or in this case, the standard error, which is given by sigma divided by the square root of n, where sigma is the standard deviation of the population and n is the sample size. So there we're just using the central limit theorem and replacing sigma and mu with the corresponding values that we get from the central limit theorem. And now I want to take this inequality, and if I multiply all terms in this inequality by the standard error, which is sigma over the square root of n, then in the middle, we cancel out that denominator, and I would multiply that 1.96 by sigma over the square root of n, and the minus 1.96 by sigma divided by the square root of n. So we're just doing some algebra in that stage. Moving to the line below, we're now subtracting x bar from all terms in that inequality. So we lose the x bar in the middle term. We get a minus x bar over here, and we also subtract x bar over here. And finally, it looks weird having this negative sign, so I can multiply all terms in this inequality by minus 1. When I do that with inequalities, we also need to reverse the order of the inequality. And so by multiplying all terms in this inequality by minus 1 and subsequently changing the direction of these inequalities, that brings us to this very last line, which gives us an interval that has a 95% chance of containing the population mean sigma. Okay, so now let's use that previous result to come back and help us construct a 95% confidence interval to estimate, in this case, mu sub wind, which is denoting the mean wind speed of all North Atlantic storms. Okay, and so this is a population parameter which is unknown. But what I do know is that this interval, that I pick a sample, it has a mean x bar. And if I go 1.96 times the standard error below that sample mean, up to 1.96 times the standard error above that sample mean, that this interval is going to have a 95% chance of capturing the population parameter mu sub wind. So I pick a sample, I calculate my sample mean x bar, I calculate the standard error of the sampling distribution for the mean using the central limit theorem, and now I can find two cutoffs, and that interval between those two cutoffs is going to have a 95% chance of capturing the population mean that I'm trying to estimate. And so using this process that we've just outlined, that requires us to find the standard error, which requires us, in this case, the estimate we're getting using the central limit theorem. So a good first question might be, can we even apply the central limit theorem in this context? And so in this context, we have a population and we actually don't know anything about the population possibly. All I know is that I picked a sample of 36 values that I've stored in this vector called my sample. And if I take a look at the shape of this sample, my sample, I can see from this histogram below that this data seems heavily skewed to the right. And since I picked this sample randomly from the population, it's likely that the population is also skewed to the right. But when we're using the central limit theorem, even if our population is skewed, we can still use the central limit theorem provided our sample is greater than or equal to 30. And in this case, our sample, my sample, had a size of 36 observations. So we can apply the central limit theorem here, even though the population is likely skewed. Okay, so we verified the assumptions required to apply the central limit theorem, that these are satisfied. So now let's try and use this interval that we observed earlier to construct a 95% confidence interval for the population mean. So heading down to question 4E, in this process of constructing this confidence interval, we need to know what the standard error is for the underlying sampling distribution for the mean. And in order to construct the standard error for the sampling distribution, this depends on two things. How large is our sample? In this case, our sample is size n is 36. And what is the spread in the population? So let's assume that we do not know what the population mean is. So we're trying to find an estimate for mu sub wins. But let's suppose we do know what the variance of the population is. So sigma squared is 650 square knots. So if we know what the population variance is, and we've got a sample of 36 observations, then from the central limit theorem, we can calculate the standard error for the sampling distribution. It's going to be the standard deviation of the population. So in this case, that's going to be the square root of 650 divided by the square root of the sample size. And so calculating this, we can use R to calculate this. We could say the square root of 650 divided by the square root of 36. And this gives us an output of 4.2492 knots. So that's describing the spread of the sample means in our sampling distribution for the mean. So this is kind of measuring how much variability we have in our sample statistics just due to the uncertainty, the randomness in sampling. So now that we've got a good estimate for the standard error of the underlying sampling distribution, we can now use the interval that we constructed earlier to generate a 95% confidence interval for the population mean. And so this interval that we observed earlier was the interval that goes from minus 1.96 times the standard error below the X bar up to 1.96 times the standard error above X bar, that this interval has a 95% chance of containing the population mean mu. So in this case, let's just recall what we know about our sample. It has size 36. It has a sample mean of 61.5 knots. We know that the variance of the population was 650. And from that, we just previously calculated that the standard error of the sampling distribution for the mean is therefore 4.2492. So I can take my observed sample mean and plug that in place of X bar. I can take my standard error and plug that into this same formula. And now I use these multiples, minus 1.96 and 1.96, to build in some margin of error into this estimate. And I'm going to calculate, I'll do these calculations in R down below. So that's 61.5. That's our sample mean that I stored in X bar. I'm going to say minus 1.96 times, and that 4.2492 was the standard error that we calculated up here. And that's going to give me my lower estimate, and then the upper estimate, I take my sample mean, but rather than subtracting that margin of error, I'm going to add that margin of error. And running this code cell, we can see we get the following output. My lower cutoff is about 53 knots, 53.2 knots, and my upper cutoff is almost 70 knots. It's 69.86 knots to be precise. So we have a 95% confidence interval for the mean that we got using the central limit theorem, which again is 53.2 knots up to 69.86 knots. Comparing this with the 95% bootstrapped confidence interval that we got, they're a little bit different, but they're pretty close estimates to each other. And the reason why they're off a little bit is they're just two different ways for approximating the underlying sampling distribution. One uses a simulation bootstrapping process, the other uses the central limit theorem. But to kind of summarize the main theorem, that if we are going to use the central limit theorem to construct a 95% confidence interval, we now have a nice formula boxed below where we can calculate the cutoffs, upper and lower cutoffs for this interval. And this avoids having to do any complex simulations. We just take some statistics that we calculate from the sample and use some formulas to crank out a 95% confidence interval.